video I'm gonna be doing 3 proofs of some things that might be handy in the future. So okay, let's read them. So I have the functions f from a to b and g from b to c, and if they're both injective, then the composition is injective. If they're both surjective, then the composition is surjective. If they're both bijective, composition is bijective, and the inverse of the composition of f composed with g, the g composed with f inverse is the inverse of f composed with the inverse of g. So let's start with the first one. Let's start proving A. So let's think first about my domain and my codomain. So g composed with f is a function that will go from the set A onto the set C. Now if I want to check the injectivity, I know that they're both injective and I want to see if the composition is injective. So what I'm going to do is I'm going to take x1 and x2, two elements in my domain, in my set A, that they both verify that g composed with f in x1 equals g composed with f in x2. What I want to do is I want to prove that this composition is injective. So I want to conclude that x1 equals x2. Let's think about this. So g composed with f in x1 equals g composed with f in x2. What does the composition mean? It meant g of x of f in x1 equals g of f in x2. Now g, so this is a hypothesis, g is injective. So g of a equals g of b. If I have this, then a equals b. Well, in particular, it's valid for f of x1 and f of x2 because in this case a, well, and b both are elements of b, and f was a function from a to b. So f of x is an element it's an element of b. Oh, then this is valid for f of x1 and f of x2. So what I can say is as g is injective, then f of x1 equals f of x2. Okay, I had g of a equals g of a of b implies a equals b. So g of f of x1 equals g of f of x2 implies f of x1 equals f of x2. But now f was also injective, so f is injective. So if I have f of a equals f of b, then I have a equals b. Oh well, I have here f of x1 equals f of x2, f is injective, so x1 equals x2. Now we started saying that the composition g composed with f in x1 equals g composed with f in x2, and we were able to conclude that x1 equals x2. Then this finishes our proof because it tells us that g composed with f is injective. Let's now read the second property. We have again the same functions g and f. They're surjective, then the composition is surjective. Okay, let's prove it. So now I'm going to prove V. Let's take a set. Again, G composed with F, let's remember, was a function that started in the set A and ended in the set C. So let's take an element here. I want to prove that this is surjective. I take an element in my codomain. So let's take set an element of C. And we know that G is surjective. Oh, okay. So as G is surjective, then there exists an element y in V. This is because G was a function from B to C. As it was surjective, then I could take an element here and always find an element in B. So there exists y in B such that g of y, equals set. And this is great, right? Because now f was a function that grabbed elements of A and took it to elements in B. And it was surjective. So in particular, for this y in B, so in particular, as f is surjective, I can find x in A that verifies that f of x equals y, where y is this one, is this y I took for my element set. So let's see what we have. I started saying set in C. I found a y in V, and then I found an x in A. So given a set in C, I was able to find an element x in A that verifies that G composed with f of x, because this is G of y equals set. And what is G composed with f of x? Well, it's G composed with f and x. Oh, well then, because of this, then I have that G composed with f is surjective. Okay, let's now read the last property we want to prove. So here we have two proofs. The first is that if f and g are bijective, then the composition is bijective. And then we have to prove how inverses work with the composition. Okay, let's go ahead and prove this. So let's prove C, and let's start with the first part. We have f and b and g, bijective. Then the composition, G composed with f, is bijective. Well, f and g are both bijective. This means that f and g are injective, and it also means that f and g are surjective. We proved before that when both are injective, then the composition is injective, and when both are surjective, then the composition was surjective. So I have that G composed with F is injective and G composed with F is surjective. So then this tells me G composed with F is bijective, and that part, all the hard work was done, so that was easy. Now what we want to prove now is we want to say that the inverse of the composition is the inverse of F composed with the inverse of G. Now let's remember what the inverse meant. So if I have F, a function that way from A to B, then F minus 1 is the inverse. If F minus 1 composed with F gives me the identity in A, and F composed with F minus 1 with the inverse gives me the identity in B. So what we would like to prove here is the same, only F is now all this composition. So first I'm gonna write G composed with F. This would be my F composed with what I think my inverse is. So composed with F inverse composed with G inverse. Now these inverses are well defined because I said that both F and G were bijective, right? So it's legal to actually write the inverse of F and the inverse of G. Now let's talk about this line. Let's start with this composition. The G composed with F is G evaluated in F of a certain element X. We want to do the composition of this with F minus 1 composed in the inverse of G for also an element X. And now this composition would be G in F in this, so it would be in the inverse of G in X. I think those parentheses are right. I have 1, 2, 3 and 1, 2, 3. Okay, so let's think about this part. Now this part is F composed with F inverse evaluated in an element. It doesn't matter if this is a function or not, it's just an element, okay? So F composed with its inverse gave me the identity in B. So this would be the identity in B of G minus 1 of X. And this is just G minus 1 in X. So what I have is G composed with G minus 1 in X. And this composition, I said today, if I had F composed with its inverse, gave me the identity in the codomain. So the codomain of G is C, because G was a function from B to C. This is G composed with G inverse in X, and this is just the identity in C. Okay, now we had a function, let's call this H, I'm gonna do it with another color. I had this, I called it H, and H inverse. So I'm in this case, I had H composed with H inverse, and what I have is the identity in C. So this gave me the identity in C, where C was the codomain of H. Oh, perfect. Okay, this is just what I wanted. Now what I have to prove is the same, only the other way around. I have H inverse, this part composed with H, with this other part. Okay, let's write that. So I want to do F inverse composed G inverse composed with G composed with F. Again, let's do this definition. So this is F inverse evaluated in the inverse of G composed with G of F of X. And again, using the definition of the composition, we have F inverse composed with G inverse composed with G of F of X. And again, let's have a look at what we have inside. So here, this is G inverse composed G evaluated in F of X. And I don't care about F of X, it's just an element of B. So G inverse composed G. Let's look at the definition of the inverse for a while. Now I'm in this case, I have G inverse composed with G, and it gives me the identity in my domain. So the domain of G is B. So this is the identity in B evaluated in F of X, and this is just F of X. So I can rewrite this as F inverse in F of X. And again, I have F inverse composed with F in an element X, and well, I'm not going to look at my definition again, I just did. This is the identity in A. Oh, okay, then again I started with this, that I can call it H inverse composed with H, and what I got was the identity in A. So H was a function, that's H is G composed with F, was a function from A to C, and I got H inverse composed with H equals the identity in A. So we were able to prove this one, and that's what ends the proof for our inverse of the composition. So with all this, then the inverse of the composition is F inverse composed with G inverse. And now I'm going to give you a problem for you to prove. And that is, again, we have F, a function from the set A to the set B, G, a function from B to C. And I want you to prove that if G composed with F is injective, then F is injective. And if this is 1 another one is G composed with F is surjective, then G is surjective. And another proof that is also very useful and will be used a lot in the Algebra 2 series, but it's good for you to start observing it as another definition of surjectivity. So this is for any function. If you want to use these domains, use them. But we say that f is surjective if, let's say that f is a function from a to b, if the image of f equals the codomain. So remember before we had a few examples where we had a set A, a set B, and the function f, and the image could be only a piece of this subset of B. Now, well, what happens is that if this subset equals B, then f is surjective. And if f is surjective, then this subset equals B. So that's a very useful proof for you to do and to practice proving some things.